Hello everyone. In the previous class we have discussed about the OS view of process environment and process control block. Let's continue this class with the discussion about process states and transition. We say a process state, it is an indicator of the nature of the current activity in a process. For a process PI, a state transition is nothing but change in the state which may be caused by the occurrence of some of the events in the system. For example, if a process PI is in running state and that process is requesting for an IO operation, then from running it will be entering into blocked state. Once that IO operation is completed, it will be entering into ready state from blocked state. That is what the change in the transitions. Generally, there are four kind of states we say. They are running, blocked, ready and terminated. So ready is the state when a CPU is currently executing instructions in the process code. Similarly, we have a state blocked. So this state will occur when the process has to wait until a resource request made by it has to be granted, or if it is wishes to wait until a specific event occurs. When we say a process is in ready state, when that process is wishing to use the CPU so that it can continue its operation, and terminated is the state when the execution of the program represented by it has completed normally or the OS has aborted it. So therefore we have totally four states. They are running, blocked, ready and terminated. So based on the states, we have a state transition diagram. So this is a transition diagram we have. So you can have running state, ready state, blocked state or terminated. So already I have said running is the state where the CPU is executing the instructions of the process. Blocked is the state when process is in wait state for the request it is maintained so that it can be granted, or if it is waiting for a specific event to occur. So ready is the state when CPU is wishing to use the process is wishing to use the CPU so that it can continue its operation, and termination is once it can get completed normally or OS has aborted it, right? So here if you take out the first state, that is running to completion, so running to terminated, it can occur when the process has completed its execution. So on the completion you can enter into terminated, or if OS has aborted then also it will be terminated. Similarly, you can go to running to blocked. When you have made or nothing but a process has made a resource request or waiting request. Then from running to ready, it will occur when that process has been preempted. So preemption is nothing but for a time being you are taking out that program. So taking out that program is nothing but it may occur because of the higher priority process has occurred, right, or the time allocated for that process has completed. In both the cases the preemption will occur. From ready to running, it will occur when you are giving the dispatching. So dispatching is nothing but you are setting up an environment for the execution of the process. Next we have blocked to ready. So blocked to ready, it will occur when the resource what you have requested has been granted or your wait has been completed. And again you have a new process which may cause you to be in ready state. Nothing but you are asking, your process is asking for the CPU so that it can continue its operation. So therefore this is the transition diagram you have, from where you can go to the different state like running to terminated, running to blocked, or running to ready, or maybe blocked to ready, ready to running, right? So this is the state transition diagram. So I have already said you. So these are the different state transition we have. So first one we have ready to running. So ready to running, it will occur when the process is dispatched and CPU starts resuming execution of its instruction. You can have a state transition from blocked to ready when a request made by the process is satisfied or the event for which it was waiting occurs. Next you can have the transition from running to ready when the process is preempted because the OS decides to schedule some other process. Next you can have running to blocked. So running to blocked means if you are asking for if your process is asking for an IO operation, or if it is requesting for memory or some other resources. Similarly, you can have running to terminated. So running to terminated is done when your process is completing its execution, right? It can be a self termination or it can be exceeding resource utilization. In both the cases you can have the state transition from running to terminated. So based on these transitions, what we have said, like what are the different states we have and how you can have the different transition from one state to another state, we have taken an example for a time sharing system. So here we are saying we have the two processes, nothing but two programs which are naming themselves as two processes P1 and P2. For the process P1, it is using a CPU burst of time 15 millisecond. CPU is 15 millisecond and it is using IO of 100 millisecond. Similarly, we have program P2. So this program P2 is again using CPU burst of around 30 millisecond and IO of around 60 milliseconds. So now we have the two programs, nothing but two processes. We have the process P1 is using a CPU burst time of 15 millisecond, right? And it is using IO time for 100 milliseconds. Similarly, we have process P2 which will be using a CPU burst of 30 millisecond and again it is using a IO burst of 60 millisecond. For simplicity, we have assumed that the process created to execute programs P1 and P2 are themselves called as P1 and P2 respectively. So now you can check out the table over here. At time 0, we are saying both the process are in ready state, and once the time has occurred, it is starting the execution for process P1 has been scheduled. Process P1 is scheduled, therefore it has marked running state, nothing but the CPU has started execution of its instruction, whereas P2 is marked ready. In the next time 10 millisecond, in the next time 10 millisecond, the P1 is preempted. So preempted is nothing but maybe it is giving the priority, so that higher priority process has occurred or the time allocated for that P1 has been over. That is why P1 is preempted and you have scheduled P2. Once you have scheduled P2, therefore it has to be marked running. Since P2 is scheduled, it will be marked running and P1 will be marked ready. At 20 millisecond, P2 is preempted. It has taken on and you are scheduling P1. Right? Since you are scheduling P1, then P1 will be in running state and P2 will be in ready state. At 25 millisecond, P1 is requesting for an IO operation. Since P1 is asking for IO operation, then it will be blocked. Right? So P1 has asked for IO operation, so it is blocked and you are scheduling P2. Since P2 is scheduled, it will be in running state. At 35 millisecond, you can see P2 is preempted and we don't have any other processes it is running. Therefore, P1 is still in blocked state and P2 is in ready state, and it will be continued for the next till the next process occurs. Therefore, P2 is scheduled. Now P1 is blocked state and P2 is in running. So all this time duration your process P1 is blocked because it has requested for an IO operation. So from running it has entered into the blocked state. So you can see here, so P2 is scheduled and again P1 is in blocked and P2 is in running state. Again at 45 millisecond P2 is asking for an IO operation. So therefore, since it is asking for IO operation, then it will enter into blocking state from running state. At this time both P1 and P2 are blocked state. At 125 millisecond there occurs an IO interrupt which is saying that the IO operation of P1, process P1 is completed. The IO operation of process P1 is completed. Therefore, the P1 becomes ready. P1 becomes ready until still your P2 is in blocked state, right? So process P1 was ready, it has been scheduled. So once it is scheduled, it will enter into the running state and still your P2 is in blocked state. So this is the example we have taken for a time sharing system.